Imagine standing on the shore of what is now the North Sea, but instead of water stretching to the horizon, you see rolling hills, dense forests, and rivers winding through valleys. Herds of mammoth graze in the distance. Small groups of humans have made their homes here, fishing the rivers and hunting the abundant game. This isn't fantasy. This was reality 12,000 years ago, before the greatest flood in human memory swept it all away. Beneath our modern oceans lie the drowned remnants of an entire world, a world where our ancestors lived, loved, built communities, and told stories around fires. What happened to this world? Why do cultures across every continent share remarkably similar stories of a great deluge that destroyed civilization and forced humanity to start anew? Tonight, we're going to explore one of the most traumatic transformations in Earth's history. The catastrophic flooding that marked the end of the last ice age. This isn't just ancient history. The events we'll discuss tonight shaped the very foundations of human civilization, triggered the agricultural revolution, and left an indelible mark on our collective memory that echoes through mythology, religion, and culture even today. As you settle in, prepare to journey back to a time when the world was remade by water, when ancient ice dams failed catastrophically, and when our ancestors witnessed changes so profound that they passed down warnings through thousands of generations. Let's begin our journey 20,000 years ago, at the height of the last ice age, when Earth was a very different planet. 20,000 years ago, during what scientists call the last glacial maximum, Earth was locked in the grip of the most recent ice age. But this wasn't the frozen wasteland that might spring to mind. Instead, imagine a planet fundamentally reorganized by ice, a world of alien and familiar, harsh yet teeming with life adapted to its challenges. Massive ice sheets dominated the northern continents. The Laurentide ice sheet covered virtually all of Canada and extended deep into what is now the northern United States. Picture ice nearly 2 miles thick. That's over 10,000 feet, stretching from the Arctic Ocean down to where New York City stands today. This single ice sheet contained enough frozen water to lower global sea levels by hundreds of feet. In Europe, the Scandinavian ice sheet buried northern Europe under similar depths of ice, while smaller glaciers covered the Alps, the Pyrenees, and mountain ranges across the continent. In the southern hemisphere, ice sheets expanded dramatically across Antarctica and Patagonia. Mountain glaciers worldwide grew to sizes that would dwarf their modern remnants. But here's what makes this period particularly fascinating. With so much water locked up in ice, sea levels were approximately 400 feet, about 120 meters lower than they are today. To put that in perspective, that's roughly the height of a 40-story building. This dramatic drop in sea level completely transformed the world's coastlines and exposed vast expanses of land that are now deep beneath the ocean. The lower sea levels created what we now call exposed continental shelves, essentially extensions of the continents that had been dry land during low sea levels throughout Earth's history. These areas weren't barren seabeds waiting to be flooded. They were fully realized landscapes with their own ecosystems, complete with forests, grasslands, rivers, lakes, and abundant wildlife. One of the most significant of these exposed areas was Beringia, the land bridge connecting Siberia to Alaska. This wasn't just a narrow strip of land. Beringia was a subcontinent in its own right, spanning hundreds of miles from north to south. It was here that humans first entered the Americas, following game animals across grasslands that now lie beneath the Bering Strait and Chukchi Sea. These early Americans had no concept that they were discovering a new continent. They were simply following food sources across continuous land. In Southeast Asia, the exposed Sunda Shelf created a massive landmass called Sundaland, connecting what are now the islands of Indonesia, Malaysia, Borneo, Java, and Sumatra into a single, vast tropical landscape. Archaeological evidence suggests this region supported significant human populations who developed maritime technologies and complex societies, most of whose remains now rest underwater. In Europe, The North Sea was largely dry land, a region now called Doggerland by archaeologists. This was a vast, low-lying plain with a major river system fed by the Thames from Britain and the Rhine from Europe. Doggerland was, by all accounts, some of the richest territory in Ice Age Europe. Gentle rolling hills, extensive wetlands, and abundant resources from both land and sea. It was a human population center, though we're only beginning to understand its full significance as underwater archaeology gradually reveals its secrets. Around the world, similar landscapes existed off every modern coast. The Persian Gulf was a river valley, a fertile lowland that may have been home to some of humanity's earliest agricultural experiments. The Mediterranean coastline extended miles beyond its present bounds. The eastern coast of North America stretched far out into what is now the Atlantic Ocean. Australia and New Guinea were connected, forming a landmass called Sahul. These weren't marginal environments. Coastal zones are typically among the most productive landscapes on Earth, offering access to both marine and terrestrial resources. The exposed continental shelves of the Ice Age would have been magnets for human settlement, supporting potentially large populations whose archaeological traces now lie beneath hundreds of feet of seawater. The climate of the last glacial maximum was not uniformly frozen. While the regions near the ice sheets experienced brutal cold, other areas had climates that, while cooler and drier than today, were quite livable. In fact, some regions that are now deserts were more hospitable during the Ice Age, with greater rainfall and more vegetation. The giant ice sheets created their own weather systems, fundamentally altering wind patterns and ocean currents. The jet stream was pushed much farther south than today, bringing different precipitation patterns to regions far from the ice. Some areas that are now lush were arid during the Ice Age, while some modern deserts had enough rainfall to support grasslands. The animal life of this period was spectacular. North America was home to woolly mammoths, mastodons, giant ground sloths that stood, 12 feet tall saber-toothed cats, dire wolves, giant beavers, the size of bears, camels, horses, and short-faced bears that would have stood 11 feet tall on their hind legs. Europe had its own megafauna: woolly mammoths and woolly rhinoceroses, cave lions, cave bears, and giant elk with antlers spanning 12 feet. Humans were well established across much of the globe by this time. They had sophisticated tools, controlled fire, created art, practiced burial rituals, and had complex social structures. They made fitted clothing from animal hides, built substantial shelters, and had developed specialized hunting strategies for taking down megafauna. These were not primitive people struggling to survive. They were successful, adapted populations with rich cultures and deep knowledge of their environments. Archaeological evidence suggests that human populations were particularly dense along coastlines, where marine resources supplemented terrestrial hunting and gathering. Fish, shellfish, seabirds, and marine mammals would have provided reliable, protein-rich food sources. The exposed continental shelves, with their rivers, wetlands, and access to the sea, would have been optimal human habitats. And here is a crucial point. Most of the archaeological evidence from these coastal populations is now underwater, lost to us unless we can conduct underwater archaeology on a massive scale. What we know about Ice Age humans comes primarily from inland sites that were less affected by sea level rise. We essentially looking at a skewed sample, like trying to understand American culture by only studying people who live in the mountains and completely ignoring everyone who lives in cities or near coasts. One of the most important features of the Ice Age landscape was something that most people today have never heard of: massive glacial lakes held back by ice dams. Understanding these lakes is crucial to understanding what happened at the end of the Ice Age, because their catastrophic release created some of the most powerful floods in Earth's history. As the ice sheets grew and advanced, they acted like enormous bulldozers, reshaping the landscape. In some places, they created natural dams, blocking river valleys and creating vast lakes behind them. The largest of these was Glacial Lake Agassiz in North America. At its maximum extent, Lake Agassiz covered an area larger than all of the modern Great Lakes combined. To visualize this, imagine a body of water covering most of Manitoba, Saskatchewan, and Ontario, and extending into the northern United States, Minnesota, North Dakota, and beyond. At various times, this single lake held more fresh water than all current lakes on Earth combined. The ice dam holding back Lake Agassiz was the southern edge of the Laurentide ice sheet itself, a wall of ice miles thick and hundreds of miles long. As long as the ice remained frozen and stable, it held back this enormous volume of water. But ice, especially ice near its melting point, is not a stable dam material. It can fracture, float, melt through, or collapse catastrophically. Similar glacial lakes existed worldwide. In northern Europe, the Baltic ice lake was impounded by ice. In Siberia, ice-dammed lakes formed in various locations. In the mountains of western North America, glacial Lake Missoula formed and reformed multiple times, each time releasing catastrophic floods. These glacial lakes represented an enormous concentration of potential energy. All of that water, held back by nothing but ice, was waiting for the moment when the ice could no longer contain it. And when that moment came, and it did come, repeatedly, the results were beyond anything in modern human experience. Around 15,000 years ago, Earth's climate began to shift. Orbital variations changes in Earth's tilt and wobble as it orbits the sun brought increased solar radiation to northern latitudes during summer months. This triggered the beginning of deglaciation, the great thawing that would eventually end the Ice Age. The melting was gradual at first. Ice sheets began to retreat from their maximum extent. In some places, meltwater carved channels through or beneath the ice. Lakes of meltwater formed on the surface of glaciers. The edges of the ice sheets became unstable, occasionally calving off enormous icebergs into the ocean. As ice melted, sea levels began to rise slowly at first, then with increasing speed as the process accelerated. The exposed continental shelves began to flood. Rivers backed up as the ocean encroached inland. Coastal communities would have noticed the changes over generations. Beaches gradually disappearing, landmarks slowly submerged, and territories shrinking. For several thousand years, this warming continued. Temperatures rose, ice retreated, vegetation zones shifted northward, and sea levels crept upward. It must have seemed like an irreversible trend climate changing in one direction, steadily and predictably. Then, around 12,900 years ago, something dramatic happened. The warming abruptly reversed. The Younger Dryas, named after an Arctic flower that reappeared in European pollen records during this period, represents one of the most abrupt climate shifts in geological history. In less than a decade, temperatures in many regions plummeted. In some areas, particularly around the North Atlantic, temperatures dropped by as much as 15 degrees Celsius 27 degrees Fahrenheit in just a few years. To put this in perspective, imagine if the climate of New York City suddenly shifted to match that of northern Labrador in less than a generation. That's the scale of change we're discussing. The effects were dramatic and widespread. Glaciers that had been retreating began advancing again. Alpine glaciers surged forward, overrunning valleys that had recently been freed from ice. The edges of the great ice sheets stabilized and in some places began to advance. Forests died back, replaced by tundra vegetation. Animals and humans retreated from regions that suddenly became uninhabitable. The Younger Dryas cold snap lasted approximately 1,300 years, from about 12,900 to 11,600 years ago. For more than a millennium, Earth was plunged back into near glacial conditions. The steady deglaciation that had been underway came to a screeching halt. In fact, the ice sheets thickened somewhat during this period, as cooler temperatures and increased snowfall allowed them to stabilize and even grow. The cause of the Younger Dryas has been one of the most debated questions in climate science. Several theories have been proposed, each with supporting evidence and passionate advocates. One hypothesis suggests a meteorite impact or airburst over North America. Proponents point to evidence of nanodiamonds, platinum anomalies, and other markers in sediments dated to the beginning of the Younger Dryas. They argue that such an impact could have thrown debris into the atmosphere, blocking sunlight and triggering rapid cooling. This theory remains controversial, with some evidence supporting it and other evidence contradicting it. Another theory invokes volcanic eruptions. Large volcanic events can inject aerosols, tiny particles high into the atmosphere, where they reflect sunlight back into space, cooling the planet. The geological record shows evidence of significant volcanic activity around the time of the Younger Dryas onset. However, identifying a single eruption large enough to trigger such dramatic cooling has proven difficult. The most widely accepted explanation involves ocean circulation and meltwater. Here's how this theory works. The Atlantic Meridional Overturning Circulation, often called the AMOC, and popularly known as the Gulf Stream system, is a conveyor belt of ocean currents that transports warm water from the tropics northward and returns cold water southward at depth. This circulation is driven partly by differences in water density. Cold, salty water is dense and sinks, pulling more water behind it. The theory suggests that a massive pulse of fresh water from melting ice sheets, possibly from a sudden drainage of glacial Lake Agassiz into the North Atlantic, disrupted this circulation. Fresh water is less dense than salt water, and enough fresh water entering the North Atlantic could have prevented the normal sinking of cold water, essentially shutting down or dramatically weakening the AMOC. Without this circulation bringing warm water northward, temperatures around the North Atlantic, and by extension, much of the northern hemisphere, plummeted. The climate system had been knocked out of one stable state into another, colder one. Evidence for this freshwater pulse hypothesis comes from ocean sediment cores, which show sudden changes in the chemistry of fossil shells that indicate rapid freshwater inputs into the ocean. The timing matches the onset of the Younger Dryas remarkably well. It's also possible that multiple factors worked together. Perhaps a meteorite impact or volcanic eruption provided an initial cooling shock, which then triggered changes in ocean circulation that sustained the cold period. Climate systems are complex, with many feedbacks and interactions, and disentangling cause from effect across millennia is challenging. Whatever the exact cause, the Younger Dryas had a profound effect on human societies worldwide. In the Middle East, archaeological evidence suggests that the cold, dry conditions of this period disrupted the wild plant harvesting that had been developing in the Fertile Crescent. Some researchers argue that this crisis actually accelerated the development of agriculture, that people began deliberately planting and tending wild grains because the climate no longer allowed them to simply gather enough wild seeds. Here's a crucial aspect of the Younger Dryas that's often overlooked. During this cold snap, the ice dams holding back glacial lakes were reinforced. Colder temperatures meant less melting, more freezing, and more stable ice. The ice sheets thickened. The dams holding back lakes like Agassiz became stronger and more robust. Meanwhile, meltwater continued to flow into these lakes from the surrounding landscape. Rivers that had been established during the earlier warming continued to drain into the ice-dammed basins. Precipitation, snow, and rain accumulated. The lakes grew deeper and more extensive. Imagine a dam with water building up behind it, the water level rising year by year, decade by decade, century by century. The dam is strong enough to hold for now, but the pressure increases relentlessly. The volume of water becomes staggering. And the material of the dam is made of ice remains fundamentally unstable, especially as climate begins to shift again. This was the situation at the end of the Younger Dryas. Behind ice dams around the northern hemisphere, truly enormous volumes of water had accumulated. Glacial Lake Agassiz was at or near its maximum extent. In Siberia and northern Europe, similar lakes waited behind ice barriers. The stage was set for catastrophe. And then, approximately 11,600 years ago, the climate shifted again, and this time, the change was even more dramatic than the onset of the Younger Dryas. The end of the Younger Dryas was as abrupt as its beginning, perhaps even more so. Ice cores from Greenland show that temperatures in the Arctic rose by perhaps 10 degrees Celsius, 18 degrees Fahrenheit in a single decade. Some estimates suggest the transition might have been even faster, possibly occurring within just a few years. This is a staggering rate of climate change. To experience this today would be like watching the climate of northern Canada transform into something resembling the American Midwest in less than a decade. Trees dying and new species taking over, animal ranges shifting hundreds of miles, and seasons changing character completely. The causes of this rapid warming are still debated, but most likely it involved the AMOC switching back on after being suppressed. During the Younger Dryas, once ocean circulation resumed, warm water flooded northward again, rapidly raising temperatures around the North Atlantic and throughout much of the northern hemisphere. The effects on the ice sheets were immediate and catastrophic. Ice that had been stable or even growing slightly during the Younger Dryas suddenly faced dramatically warmer temperatures, especially in summer. Melting accelerated rapidly. Surface meltwater on glaciers increased dramatically. Rivers of meltwater carved deeper channels through and under the ice. Most critically for our story, the ice dams holding back glacial lakes began to fail. To understand what happened next, we need to understand how ice dams fail and why their failure tends to be catastrophic rather than gradual. Ice may seem solid, but it actually flows like a very slow liquid, especially when it's thick enough and warm enough. When ice is cold well below freezing, it's relatively strong and rigid. But as it approaches the melting point, it becomes increasingly plastic and weak. An ice dam holds back water through a combination of its own structural strength and the friction between the ice and the valley, walls or terrain it is resting on. As water pressure behind the dam increases, it exerts enormous force on the ice. If there's any weakness, a crack, a channel of flowing water through or under the ice, or a warm spot where melting is faster, that weakness can rapidly expand. Water has a remarkable property. It can find and exploit any weakness. If water begins to flow through or under an ice dam, it carries heat energy with it. This flowing water melts the ice it contacts, creating a larger channel, which allows more water to flow, which melts more ice, creating an even larger channel, and so on. This is a positive feedback loop, a runaway process that accelerates exponentially. Once an ice dam begins to fail, the failure typically cascades rapidly and completely. Within hours or days, the entire dam can disintegrate, releasing all the water behind it in a catastrophic flood. This isn't speculation. We have modern examples of ice dam failures, though none at the scale of those at the end of the Younger Dryas. We also have geological evidence, landscape features that could only have been carved by. Water flows beyond anything in modern experience. The best studied example of Ice Age catastrophic flooding is the series of events called the Missoula Floods, also known as the Channeled Scablands. Floods which occurred in the Pacific Northwest of North America. Glacial Lake Missoula formed when a lobe of the Cordilleran ice sheet blocked the Clark Fork River in what is now Montana. Behind this ice dam, a lake formed that at its maximum extent was half the size of Lake Michigan, with a depth of over 2,000 feet, in some places deeper than the Grand Canyon. Geological evidence shows that this ice dam failed catastrophically dozens of times over thousands of years. Each time, the lake would drain in a matter of days or even hours, sending an unimaginable volume of water surging westward across what is now Idaho and Washington. The peak discharge of these floods has been estimated at up to 17 cubic miles of water per hour. To put this in perspective, that's more than 10 times the combined flow of all rivers on Earth today. The water moved at speeds estimated at 65 miles per hour, the speed of a car on a highway. But With a depth of hundreds of feet, the evidence left behind is spectacular. The channeled scablands of eastern Washington are a landscape of enormous channels carved through solid bedrock, giant gravel bars, hundreds of feet high ripple marks, with wavelengths of hundreds of feet, and boulders the size of houses carried dozens of miles from their sources. This landscape was dismissed as impossible by geologists for decades until the evidence became overwhelming. No other explanation could account for these features. They required water flows far beyond anything in modern experience. The Missoula floods carved the Columbia River Gorge, deepened it dramatically, and sent water surging westward to the Pacific Ocean. Temporarily, these floods raised sea level in the Pacific and created massive backflows of water up tributary valleys. Now imagine floods not just from glacial Lake Missoula, significant as those were, but from glacial Lake Agassiz, which was dozens of times larger. As the Younger Dryas ended and rapid warming began, the ice dam containing Lake Agassiz, the southern margin of the Laurentide ice sheet, began to fail. Exactly when and how this happened remains an area of active research, but the evidence suggests there were multiple catastrophic drainage events. Some of these drainage events sent water north through various outlets, eventually reaching the Arctic Ocean through what is now the Mackenzie River system. Others sent water east through the Great Lakes Basin and down the St. Lawrence River to the North Atlantic. Still others may have sent water south, down the Mississippi River system to the Gulf of Mexico. Each of these drainage routes would have experienced floods that dwarf the Missoula events. We're talking about water volumes, measured not in cubic miles per hour, but potentially in hundreds of cubic miles over a period of days or weeks. The landscape through which this water flowed was scoured, reshaped, and fundamentally altered. Ocean sediment cores show evidence of these massive freshwater pulses. Suddenly, in layers dated to around 11,600 years ago, and again around 11,300 years ago, the chemistry of the ocean changes dramatically, indicating enormous inputs of fresh water. These pulses were large enough to temporarily alter ocean salinity across vast areas. The fresh water from these floods disrupted ocean circulation, possibly triggering shorter cold periods, even as the overall trend was warming. The sudden addition of so much fresh water to the North Atlantic may have caused temporary slowdowns in the AMOC, creating brief cold snaps superimposed on the longer-term warming trend. North America wasn't the only region experiencing catastrophic floods. Similar events occurred wherever large ice-dammed lakes existed. In Europe, the collapse of ice dams released floods that carved valleys and transported massive boulders across the landscape. The Baltic ice lake, when it finally drained, dropped by dozens of meters in a relatively short period, with catastrophic effects on anything downstream. In Siberia, the evidence is less well studied, but geological markers suggest similar events occurred as ice dams failed across northern Asia. Even in regions without ice dams, the rapid melting of ice sheets created enormous rivers of meltwater. The Mississippi River, fed by meltwater from the Laurentide ice sheet, would have been vastly larger than today, a miles-wide torrent carrying icebergs, sediment, and massive volumes of water to the Gulf of Mexico. These meltwater floods were fundamentally reshaping the continents. Valleys were carved, sediment was deposited in massive deltas, and river courses were established that persist to this day. The landscape of the Northern Hemisphere, particularly in North America and Europe, bears the permanent scars of this period of catastrophic water flow. One of the most difficult things for us to grasp today is the speed at which these events unfolded. We're used to geological changes happening slowly, mountains rising over millions of years, rivers carving canyons over millennia. But the floods at the end of the Ice Age operated on human timescales. A catastrophic ice dam failure could occur within a single day. The resulting flood might last days or weeks. The landscape could be completely transformed within a single human lifetime, or even within a single year. For people living through these events, the world would have changed with terrifying rapidity. Land they had known their entire lives could be scoured away in a flood. Rivers could change course overnight. Lakes could appear or disappear in days. And these weren't isolated events. Multiple ice dams could fail in sequence, creating waves of flooding. As one lake drained, it might destabilize ice dams downstream, creating a cascade of failures. The geological record suggests this kind of cascading failure did occur in some regions. The human cost of these floods is difficult to estimate, but it must have been significant. Any communities located downstream from ice-dammed lakes or in valleys that carried meltwater would have been in grave danger. Even communities not directly in the path of floods would have been affected by the rapid landscape changes, disruptions to food sources, and displacement of people from flooded areas. While the catastrophic ice dam failures created dramatic, short-term floods, the longer-term process of deglaciation was causing a flood of a different kind, one that, while slower, was even more consequential for humanity. The steady, relentless rise of sea level. As ice sheets melted, the water had to go somewhere, and that somewhere was the ocean. Over a period from about 15,000 years ago to about 7,000 years ago, global sea levels rose approximately 400 feet, about 120 meters. This wasn't a steady rise, but rather occurred in pulses, with periods of rapid increase alternating with periods of relative stability. The major pulses of sea level rise are called meltwater pulses by scientists, and they correspond to catastrophic phases of ice sheet collapse. The most significant of these were Meltwater Pulse 1 around 14,600 years ago, which saw sea levels rise, perhaps, 50 feet in less than 500 years, and possibly much faster, and Meltwater Pulse 1b around 1,300 years ago, which occurred shortly after the end of the Younger Dryas. To understand what a 400-foot rise in sea level means, consider that this is roughly the height of a 40-story building. Every coastal area on Earth, every beach, every river mouth, every coastal plain that was less than 400 feet above the Ice Age sea level is now underwater. Given that most coastal areas are relatively flat, this meant that hundreds of miles of coast were inundated in some regions. Let's consider what this meant for specific regions around the world. Doggerland, the plain connecting Britain to continental Europe, was gradually submerged. At first, the rising sea would have created a coastline of estuaries, marshes, and mudflats. As sea level continued to rise, this coastline would have moved steadily inland. Rivers that once flowed across Doggerland to drain into the Atlantic would have become estuaries, then arms of the sea, and completely submerged channels. The final inundation of Doggerland was likely accelerated by a catastrophic event around 8,200 years ago, called the Storegga Slide, an underwater landslide off the coast of Norway that generated a massive tsunami. This tsunami swept across the North Sea, and while Doggerland was already largely submerged by this time, the tsunami likely devastated any remaining settlements and completed the transformation of this once habitable land into seabed. Today, fishermen in the North Sea occasionally bring up evidence of Doggerland in their nets: stone tools, mammoth bones, and even pieces of worked wood. Underwater archaeology has begun to map this drowned landscape, revealing river channels, ancient shorelines, and the outlines of what must have been a richly inhabited region. Sundaland, in Southeast Asia, suffered a similar fate. This vast lowland region, which had connected Indonesia, Malaysia, and nearby areas into a single landmass, was progressively flooded as sea levels rose. At various points during this flooding, large islands would have remained, gradually shrinking as the water rose. The final submersion of major areas probably occurred around 7,000 years ago. The loss of Sundaland may have been particularly significant for human history. Some researchers have speculated that this region, with its favorable climate, rich resources, and large area, may have been home to advanced societies during the late Ice Age. If so, most evidence of these societies now lies beneath the ocean. The populations living in Sundaland would have been forced to retreat to higher ground over many generations, concentrating in the areas that are now the mountainous islands of Indonesia and Malaysia. Around the world, similar stories unfolded. The Persian Gulf was once a river valley, with the Tigris and Euphrates, rivers joining with other rivers from the Iranian plateau to create a major river system draining into what was then a much smaller gulf. As sea level rose, this valley flooded, creating the Persian Gulf we know today. The speed of this flooding has been estimated at about a mile per year, in some places imperceptible day to day, but dramatic over a human lifetime. The Black Sea experienced perhaps the most dramatic flooding event of all. The Black Sea Basin was once a large freshwater lake, sitting well below sea level, but isolated from the Mediterranean by a land barrier at what is now the Bosporus Strait. Around 7,600 years ago, rising Mediterranean waters finally breached this barrier. The resulting flood has been called one of the greatest natural disasters in human history. Water from the Mediterranean cascaded into the Black Sea Basin in a waterfall that would have been dozens of times larger than Niagara Falls. Estimates suggest the Black Sea's level rose by hundreds of feet at a rate of about 6 inches per day. Coastlines would have receded by a mile or more in a single day in some places. Archaeological evidence shows that human settlements around the Black Sea were abandoned at this time, with refugees fleeing to surrounding highlands. Some researchers have suggested that this flood is the historical basis for the biblical Noah's Ark story and similar flood myths in the region, though this remains debated. The rising sea had profound effects on human populations worldwide. As we noted earlier, coastal zones tend to be highly productive environments, and they likely supported significant populations during the Ice Age. As seas rose, these populations were forced to move. Unlike a sudden flood from an ice dam failure, which would have been catastrophic, but localized, the rising sea was a slow-motion disaster that played out over thousands of years and affected every coast on Earth. But slow is relative. A rise of 1 foot per century would have been barely noticeable in a human lifetime. But a rise of 10 or 20 feet per century, which occurred during the meltwater pulses, would have been dramatic and disruptive. Consider a coastal village where people had lived for generations. The beach where they collected shellfish is slowly disappearing. The peninsula where they built their homes is becoming an island. The river mouth where they fished is becoming an estuary, then a bay, and then too deep and salty for the fish they've always caught. Within a few generations, the entire landscape has changed, and the village must move or fundamentally change its way of life. Multiply this scenario by thousands of communities around the world, and you begin to get a sense of the scale of disruption. Millions of people, perhaps a significant fraction of Earth's total human population at the time, would have been displaced over the course of millennia. Where did these coastal refugees go? Inland, necessarily. And this movement inland would have brought them into territories already occupied by other groups. This concentration of population in smaller areas would have increased competition for resources, driven social change, and possibly sparked conflicts. Some researchers argue that this coastal displacement was one of the key factors driving the Neolithic Revolution, the transition from hunting and gathering to agriculture and settled life. Faced with less territory, reduced access to marine resources, and increasing population density, human groups may have had little choice but to intensify their food production strategies. The fertile river valleys of the Tigris-Euphrates, the Nile, the Indus, and the Yellow River became focal points for human settlement. These weren't necessarily the most pleasant places to live. River valleys can be hot, humid, and prone to seasonal flooding, but they offered something crucial: reliable water and rich soils for agriculture. The development of agriculture required new technologies and social structures. Irrigation systems had to be built and maintained. Crops had to be planted, tended, and harvested in coordinated ways. Food surpluses had to be stored and distributed. All of this required cooperation, On a scale beyond the family or clan, it required larger social units, specialization of labor, and eventually, the emergence of what we recognize as civilization. The first cities, the first writing systems, and the first centralized governments all emerged in these river valleys in the millennia following the end of the Ice Age floods. It's probably not a coincidence that these developments occurred where and when they did. The rising seas had forced humanity into a corner, and in responding to that challenge, we transformed ourselves and our world. One of the most powerful tools scientists have for understanding past climate is ice cores, long cylinders of ice drilled from glaciers in Greenland, Antarctica, and other ice-covered regions. Ice forms in layers, with each year's snowfall creating a distinct band. In places where ice accumulates but rarely melts, these layers preserve a record going back hundreds of thousands of years. By carefully drilling through the ice and extracting cores, scientists can examine these layers and read them like the pages of a book. What can ice cores tell us? An enormous amount. The ice itself contains bubbles of ancient air, trapped when the snow compressed into ice. By analyzing these bubbles, scientists can determine what the atmosphere was like when that snow fell, how much carbon dioxide, methane, and other gases it contained. The ice also contains isotopes, different forms of elements, whose ratios change depending on temperature. Specifically, the ratio of heavy to light oxygen isotopes in the ice molecules themselves acts as a thermometer, telling us how cold or warm it was when that snow fell. Ice cores from Greenland have revealed the Younger Dryas with stunning clarity. The transition from warming to sudden cold appears in the ice as a sharp shift in isotope ratios, occurring over just a few years of snowfall, a blink of an eye in geological time. Similarly, the end of the Younger Dryas appears as an equally abrupt shift back to warmer conditions. These cores also show evidence of massive dust storms during cold periods, volcanic eruptions that injected particles into the atmosphere, and even potential evidence of meteorite impacts. They're an extraordinarily detailed record of climate and environmental change, with resolution down to individual seasons in some cases. Cores from Antarctica provide a southern hemisphere perspective and allow scientists to compare how climate changes in different parts of the world, whether they happen simultaneously or with delays, and whether they were global or regional phenomena. While ice cores tell us about atmospheric conditions and temperature, ocean sediment cores reveal what was happening in the seas. The ocean floor accumulates sediment steadily, dust blown from continents, volcanic ash, the shells of tiny marine organisms, and organic matter that sinks from the surface waters. Like ice, this sediment builds up in layers, creating a chronological record. By extracting cores from the ocean floor and analyzing them layer by layer, scientists can reconstruct ocean conditions thousands or millions of years ago. The shells of tiny organisms called foraminifera are particularly useful. Different species live in water of different temperatures and salinities, so by identifying which species are present in each layer, scientists can infer ocean conditions. The chemistry of these shells is also informative. Like ice, they contain isotopes whose ratios depend on the water temperature and ice volume on land. During ice ages, when water is locked up in ice sheets, the ocean becomes slightly saltier and the isotope ratios shift. When ice melts and water returns to the ocean, the ratios shift back. Most crucially for understanding the floods at the end of the Ice Age, ocean cores show evidence of massive freshwater pulses. These appear as sudden changes in the isotope ratios of shells changes that indicate large volumes of freshwater suddenly entering the ocean. The timing and location of these freshwater pulses can be matched to the drainage of specific glacial lakes. Cores from the North Atlantic show particularly dramatic evidence. Layers corresponding to the time around 11,600 years ago contain shells and sediments indicating massive influxes of cold freshwater. Exactly what would be expected from the catastrophic drainage of glacial Lake Agassiz into the North Atlantic. These cores also show evidence of Heinrich events, massive releases of icebergs from the ice sheets, which melted as they drifted south, leaving behind distinctive layers of sediment containing rocks and pebbles that could only have been transported by ice. The geological evidence for catastrophic flooding is written across the landscape, particularly in North America, but also in Europe and other regions. The channeled scablands of eastern Washington state are the most spectacular example. This landscape covering thousands of square miles looks unlike anywhere else on Earth. It's a maze of deep channels carved through solid basalt bedrock, with cliffs hundreds of feet high, massive gravel bars, and bizarre features called giant current ripples. Giant current ripples look like the ripples you might see in sand at a beach, except they wreathe 30 feet high and have wavelengths of hundreds of feet. These could only form under moving water at incredible depth and velocity. The gravel bars contain boulders the size of small houses, transported dozens of miles from their sources. The erosion patterns show water moving at speeds and depths that no modern river could match. For decades, the origin of the scablands was a mystery. In the 1920s, geologist J. Harlan Bretz proposed they were carved by catastrophic floods from glacial Lake Missoula. His ideas were ridiculed by the geological establishment of the time, who insisted that geological processes had to be slow and gradual. It took decades of accumulated evidence to prove Breitkreuz right. Similar features exist elsewhere. In Canada, the landscape bears the marks of meltwater from the Laurentide ice sheet. In Montana and Alberta, ancient flood channels and erratics, boulders transported far from their sources, mark the paths of catastrophic floods. In Europe, features in northern Germany, Poland, and Scandinavia show evidence of massive meltwater flows. The Baltic region, in particular, shows numerous channels and valleys that could only have been carved by enormous water flows during the Ice Age. Some of the most exciting evidence comes from a relatively new field, underwater archaeology. As diving technology has improved and underwater survey methods have developed, archaeologists have begun exploring the submerged continental shelves. What they're finding is remarkable. Off the coast of Denmark, archaeologists have discovered prehistoric settlements, including the remains of structures, tools, and even ancient DNA preserved in submerged sediments. These sites date to the period just before they were flooded by rising seas. In the North Sea, systematic surveys using sonar and other remote sensing technologies have mapped extensive areas of the Doggerland landscape. River channels, coastlines, and even possible settlement sites have been identified. Stone tools, animal bones, and plant remains recovered from the seabed confirm that this was once a richly inhabited landscape. Off the coast of India, the search for the legendary city of Dwarka said, in Hindu tradition, to have been swallowed by the sea has revealed submerged structures that may be ancient settlements, though their exact age and nature remain debated. In the Black Sea, surveys have found ancient shorelines now deep beneath the surface, with evidence of human activity along those shores. While the famous claim of finding Noah's Ark on a submerged beach has been debunked, genuine archaeological remains have been discovered that document the flooding of the Black Sea basin. Around the Americas, underwater surveys off both coasts have begun to reveal evidence of pre-Columbian settlements now beneath the waves. Off Florida, sinkholes that were freshwater springs during the Ice Age have yielded evidence of human activity, including tools and the remains of extinct animals. This field is still in its infancy. The technical challenges of underwater archaeology are enormous, and only a tiny fraction of the submerged continental shelves have been explored. But what has been found so far suggests that much of human prehistory lies beneath the waves, waiting to be discovered. All of this evidence, from ice cores, ocean cores, landscapes, and underwater sites, has to be dated to construct a coherent timeline of events. Several dating methods are used, each with its own strengths and limitations. Radiocarbon dating is the workhorse method for events within the past 50,000 years. Organic materials would, bone, shells contain radioactive carbon-14, which decays at a known rate. By measuring how much carbon-14 remains, scientists can determine how old the sample is. However, radiocarbon dating requires careful calibration because the amount of carbon-14 in the atmosphere has varied over time. Tree ring records, which can be counted back thousands of years, provide a calibration curve that makes radiocarbon dates more accurate. For ice cores and ocean cores, dating is done by counting layers, like counting tree rings, and by matching distinctive events, volcanic eruptions. For example, that can be dated independently and show up in multiple cores. Other methods, like measuring the decay of other radioactive elements, examining the alignment of magnetic minerals, which records Earth's changing magnetic field, and analyzing sediment accumulation rates, all contribute to building a comprehensive timeline. The result is a remarkably detailed chronology. Scientists can now say with confidence that the Younger Dryas began approximately 12,900 years ago and ended approximately 11,600 years ago. They can date the major meltwater pulses, the drainage events of glacial lakes, and the flooding of specific landscapes to within a few centuries, and in some cases, within decades. This precision allows for the correlation of events worldwide. Scientists can see how climate changes in Greenland are related to changes in Antarctica, how flooding in North America affected ocean circulation in the Atlantic, and how all of these factors influenced human societies around the globe. One of the most striking aspects of studying the end of the Ice Age is the realization that flood myths appear in cultures across the globe. More than 200 different cultures have traditional stories about a great flood that destroyed the world or threatened humanity's existence. These stories share remarkable similarities, despite arising in cultures that had no contact with each other. Common themes include waters rising to cover the land divine, warning to a chosen individual or family, construction of a boat or vessel, for survival, the saving of animals' waters, gradually receding, and the repopulation of the earth by the survivors. The most famous flood story in Western culture is the biblical account of Noah's Ark. According to this story, God decided to flood the earth because of human wickedness, but warned Noah to build an ark. Noah constructed a massive vessel, brought aboard his family and pairs of animals, and survived a flood that covered even the highest mountains. After the waters receded, Noah's descendants repopulated the earth. But this story has clear antecedents in earlier Mesopotamian literature. The Epic of Gilgamesh, one of the oldest known works of literature, includes a flood story that's strikingly similar. In this version, the gods decide to destroy humanity with a flood, but one god warns Utnapishtim, who builds a large boat and survives with his family and animals. After the flood, Utnapishtim is granted immortality by the gods. Even older than Gilgamesh is the Sumerian flood story featuring Zu-Suda, which dates to around 2000 BCE, but likely preserves much older oral traditions. In Hindu tradition, the story of Manu tells of a great flood sent by the gods to destroy the world. A small fish, actually the god Vishnu in disguise, warns Manu of the coming deluge. Manu builds a large boat, and when the flood comes, the fish, now grown enormous, tows the boat to safety on a mountaintop. Greek mythology includes the story of Deucalion and Pyrrha. When Zeus decides to destroy humanity with a flood, Deucalion, warned by his father Prometheus, builds a chest and survives with his wife. After the flood, they repopulate the earth by throwing stones behind them, which transform into people. Chinese mythology features the legendary figures of Gun and Yu, who battled against catastrophic floods. Gun attempted to stop the floods by building dams, but failed. His son, Yu, succeeded by dredging channels to drain the floodwaters, and became a heroic figure credited with founding the Xia dynasty. Native American cultures across both continents have flood stories. The Anishinaabe, Ojibwe, people tell of a great flood from which only a few people survived by building a raft. The Tlingit of Alaska have stories of flood survivors who took refuge on mountaintops. The Caddo people of the southern United States tell of a time when waters covered the land and only those on a high mountain survived. In South America, Amazonian peoples, Andean cultures, and others have flood traditions. The Mapuche of Chile tell of a battle between two giant serpents that caused catastrophic flooding. The Muisca people of Colombia have legends of floods that destroyed earlier civilizations. Australian Aboriginal peoples have stories of rising seas drowning coastal lands. These stories are particularly remarkable because they appear to preserve memories of specific geographical features, islands, coastlines, landmarks that have been submerged for thousands of years. When scientists have investigated these claims, they've found that Aboriginal flood stories accurately describe landscapes that have existed above water for 7,000 years or more. In the Pacific Islands, many cultures have flood stories, despite living on islands where a global flood would have left nowhere to survive. These stories may preserve memories of tsunamis, local flooding events, or for those whose ancestors migrated from Southeast Asia, memories of the flooding of Sundaland. For centuries, flood myths were generally dismissed by scholars as purely mythological, either complete fabrications, heavily embroidered accounts of local floods, or literary borrowings between cultures. The idea that they might preserve actual memories of prehistoric events was considered fanciful. But the accumulated evidence for the catastrophic flooding at the end of the Ice Age has caused many researchers to reconsider. Could these stories actually be cultural memories of real events? Several factors support this interpretation. First, the timing is right. The major flooding events occurred between about 15,000 and 7,000 years ago, well within the span of oral tradition. Australian Aboriginal cultures are known to preserve accurate geographical knowledge for at least 10,000 years. If humans can remember landscape features that long, they could certainly remember dramatic events like catastrophic floods. Second, the geographical distribution of flood myths matches the distribution of flooding. The myths are most elaborate and detailed in regions that experience the most dramatic flooding. Mesopotamia, flooded Persian Gulf River Valley. The Eastern Mediterranean, Black Sea flooding. South and Southeast Asia, flooding of Sundaland and coastlines. Northern Europe, flooding of Doggerland and the Baltic, and coastal regions of the Americas. Third, some flood stories contain details that match geological evidence surprisingly well. The Mesopotamian flood stories, for instance, describe a flood coming from the south consistent with the Persian Gulf flooding as sea levels rose. Aboriginal stories describe specific geographical features being drowned, features that archaeology and geology confirm were indeed submerged. Fourth, the variations between different cultures' flood stories suggest these aren't all borrowed from a single source, but rather developed independently based on local experiences. The Mesopotamian flood features a river valley setting. The Greek flood occurs in mountainous terrain. The Southeast Asian stories involve island landscapes, and so on. However, there are also arguments against interpreting all flood myths as memories of Ice Age events. Some researchers point out that floods are universal human experiences. Every culture experiences floods to some degree. So flood myths might simply reflect the universal human fear of water and loss of control. Additionally, many flood myths contain elements that clearly aren't literal history. Divine interventions, animals speaking, and magical transformations. This suggests that even if the stories began with real events, they've been heavily mythologized. The truth probably lies somewhere in between. Flood myths likely have multiple origins. Some may indeed preserve memories of the post-Ice Age floods. Others might commemorate more recent local flood events. Still others might be purely symbolic or mythological, using flood imagery to explore themes of destruction and renewal. But the sheer number of flood stories, their global distribution, and their common elements suggest that something real underlies at least some of them. The hypothesis that humanity as collective memory preserves accounts of the great floods at the end of the ice. Age is no longer considered fringe speculation. It is a legitimate scientific question being actively investigated. How could memories of events 12,000 years ago be preserved? Understanding this requires looking at how oral traditions work and how cultural memory operates. In traditional societies without writing, knowledge is preserved through oral tradition stories, songs, ceremonies, and rituals passed down from generation to generation. We often underestimate the accuracy and longevity of oral tradition, probably because our own culture relies so heavily on written records. But in societies where oral tradition is the primary method of preserving important knowledge, tremendous care is taken to maintain accuracy. Stories are told and retold, often in formal settings with specific ritual significance. Errors are corrected by other knowledge holders. Mnemonic devices, rhythms, rhymes, and repetitive phrases help ensure accurate transmission. Professional storytellers or knowledge keepers often undergo years of training. In many cultures, being a keeper of oral history is a sacred responsibility, and the accuracy of transmission is a matter of great importance. Researchers have documented oral traditions that accurately preserve information for impressive spans of time. Land boundaries, genealogies, historical events, and even astronomical observations have been shown to be preserved accurately for centuries or even millennia in various cultures. Events that are particularly dramatic or significant are more likely to be remembered and passed down. A catastrophic flood that destroyed known landscapes and displaced populations would certainly qualify. Such events would be told and retold, becoming foundational narratives in a culture's understanding of the world and its history. As these stories are passed down, they inevitably change and are reinterpreted in light of current beliefs and values. Divine explanations might be added after all. From a pre-scientific perspective, how else could such a catastrophe be explained? Moral lessons might be incorporated. Details might be embellished or forgotten. But the core of the story, a great flood, the destruction of known lands, the displacement of people, the transformation of the world, could remain intact even as the details changed. This is what we seem to see in many flood myths, a core of potentially historical truth wrapped in layers of mythological and cultural interpretation. One specific case deserves special attention: the flooding of the Black Sea basin around 7,600 years ago. Some researchers have proposed that this event might be the historical basis for the Noah's Ark story and related flood myths in the region. Before the flood, the Black Sea was a large freshwater lake, lying well below sea level. People lived around its shores, fishing and farming the rich lands around the lake. Then, as Mediterranean sea levels rose to the point where they topped the natural barrier at the Bosporus, a catastrophic influx began. Water from the Mediterranean cascaded into the Black Sea basin in volumes estimated at about 40 cubic miles per day, equivalent to 200 Niagara Falls. The Black Sea's water level rose rapidly, perhaps 6 inches per day. Coastlines retreated by as much as a mile per day in some places. For people living around the Black Sea, this would have been terrifying and inexplicable. The waters of the lake they had known their entire lives were rising, day after day, week after week, destroying settlements and forcing everyone to flee to higher ground. The flood continued for perhaps a year or more before the Black Sea reached equilibrium with the Mediterranean. Archaeological evidence shows that settlements around the Black Sea, dating to before 7,600 years ago, are now underwater, while new settlements appear in the surrounding highlands after that date, exactly what would be expected if a massive flood displaced the coastal population. Some researchers argue that survivors of this flood, displaced from their homes, migrated outward from the Black Sea region, taking their flood story with them. They suggest this could explain the spread of similar flood stories through the Middle East and Europe, and eventually into the biblical tradition. This theory remains controversial. Critics point out that the biblical flood story has clear literary antecedents in Mesopotamian texts that predate the Black Sea flood. Others argue that the Black Sea flood, while dramatic, wouldn't have seemed like a world-ending event to people who could simply move inland. But whether or not the Black Sea flood specifically inspired the Noah story, it demonstrates that catastrophic flooding events of the kind described in flood myths did actually occur in regions where these myths are found and at times that fall within the range of oral tradition. The end of the Ice Age floods didn't just change the physical landscape, they fundamentally altered human society. Understanding how requires thinking about population distribution and resource availability. During the Ice Age, when sea levels were low and continental shelves were exposed, human populations were dispersed across a larger land area. Coastal zones, with their rich marine and terrestrial resources, supported significant populations. Inland regions had lower population densities. As seas rose, coastal populations were compressed into smaller areas. This happened gradually over thousands of years, but the result was a steady increase in population density in the remaining habitable zones. Higher population density creates social pressures. More people competing for the same resources leads to conflicts. Territory becomes more valuable. Traditional hunting and gathering strategies may no longer provide enough food for growing populations in shrinking territories. Under these pressures, human societies had to adapt or face collapse. The adaptations they developed would lay the foundations for civilization as we know it. The transition from hunting and gathering to agriculture, what archaeologists call the Neolithic Revolution, occurred independently in several regions around the world, beginning shortly after the end of the Ice Age. In the Middle East, this transition began around 12,000 years ago in the Fertile Crescent. In China, agriculture developed in the Yellow River Valley around 10,000 years ago. In Mesoamerica, in the Andes, in West Africa, and in New Guinea, all of these regions saw the independent development of agriculture between about 10,000 and 4,000 years ago. The timing is striking. For hundreds of thousands of years, humans had been hunter-gatherers. Then, within a few thousand years after the Ice Age floods, multiple human societies independently began farming. Why? Traditional explanations have focused on climate. The end of the Ice Age brought a warmer, more stable climate that made agriculture feasible. This is certainly part of the answer. But it doesn't fully explain why agriculture developed when and where it did. The population pressure hypothesis suggests that rising sea levels and the displacement of coastal populations created conditions that made agriculture necessary. With more people concentrated in smaller areas, hunting and gathering couldn't provide enough food. People needed to intensify food production. In the Fertile Crescent, archaeological evidence suggests that people had been gathering wild grains for thousands of years. But around 12,000 years ago, they began deliberately planting and tending these grains. Why the shift? Possibly because changing conditions, including the Younger Dryas cold snap and subsequent climate instability, made wild harvesting less reliable. Or possibly because population pressure from displaced coastal populations made intensification necessary. Similar patterns appear elsewhere. In each region where agriculture developed, there's evidence of population growth and increasing social complexity in the periods just before farming began. Agriculture required sedentism, staying in one place rather than moving seasonally. It required planning ahead, storing food, and cooperating in larger groups. These requirements led to profound social changes. Agriculture could be practiced in many environments, but it flourished especially in river valleys. The Tigris-Euphrates Valley in Mesopotamia, the Nile Valley in Egypt, the Indus Valley in Pakistan and India, the Yellow River Valley in China, and the Niger Valley in West Africa. All of these became centers of early civilization. River valleys offered several advantages for agriculture. Regular flooding deposited nutrient-rich silt on fields, maintaining soil fertility. Rivers provided reliable water for irrigation. The flat terrain was easy to farm, and rivers served as transportation routes, facilitating trade and communication. But river valleys also presented challenges. Seasonal flooding could be destructive as well as beneficial. Rivers needed to be managed, dammed, dredged, and channeled to be fully useful for agriculture. This required coordinated labor on a large scale. Managing water became a central organizing principle for early civilizations. Irrigation systems had to be built and maintained. Floodwaters had to be controlled and directed. Water rights had to be allocated and disputes resolved. All of this required social complexity beyond the level of family or clan. Some scholars have argued that the need to manage water was the primary driver for the development of centralized government. Early states arose, in this view, as water management authorities, governments whose legitimacy rested on their ability to control flooding, provide irrigation, and ensure water supplies. Whether or not this is the complete explanation, it's clear that early civilizations did focus intensely on water management. The great cities of Mesopotamia were built around elaborate canal systems. Egyptian civilization organized around the Nile and its annual flood cycle. The Indus Valley civilization built sophisticated drainage and water supply systems. Early Chinese states managed the Yellow River and controlled its devastating floods. Agriculture and sedentism led to other changes. Permanent settlements meant that people could accumulate possessions. They no longer had to carry everything they owned. This allowed for specialization. Not everyone needed to be engaged in food production. Some people could become artisans, making pottery, weaving cloth, or working metal. Others could become traders, priests, administrators, or soldiers. This specialization led to social stratification. In hunter-gatherer societies, everyone has roughly equal status, though with variation based on age, gender, and individual skills. But in agricultural societies, differences in wealth and power become more pronounced. Those who control land, water rights, or food storage gain power over others. The archaeological record shows this increasing complexity clearly. Early agricultural villages are relatively simple and egalitarian. But within a few thousand years, we see the emergence of larger settlements with clear evidence of social hierarchy. Larger houses for elites, monumental buildings, rich burials, and fortifications. Writing emerged as a tool for managing complex societies. The earliest writing systems, cuneiform in Mesopotamia, hieroglyphics in Egypt, and oracle bone script in China, were developed primarily for administrative purposes, recording harvests, tracking inventory, documenting transactions, and recording tax payments. Mathematics developed for similar reasons. Measuring fields, calculating harvests, allocating water, and planning construction projects all required mathematical knowledge. The earliest mathematical texts we have are practical handbooks for administrators and engineers. Organized religion also became more complex. While hunter-gatherers had rich spiritual traditions, agricultural societies developed formal priesthoods, temples, and complex ritual cycles tied to agricultural seasons. Priests gained power as intermediaries between humans and the forces controlling floods, droughts, and harvests. All of these developments, agriculture, sedentism, social hierarchy, specialization, writing, mathematics, organized religion, and centralized government emerged in the centuries and millennia following the end of the Ice Age floods. While the floods didn't directly cause these changes, they created conditions that made them more likely. Displaced populations, increased population density, competition for resources, and the need for cooperation and organization on larger scales. While celebrating the rise of civilization, it's worth considering what was lost in the transition. The drowned coastlines contained not just land, but human history settlements, tools, art, and the remains of thousands of years of human activity. We can never fully know what Ice Age coastal societies were like, because most of their remains are underwater. But what little underwater archaeology has revealed suggests they were sophisticated, with complex technologies and rich cultural traditions. Many archaeologists now believe that our picture of Ice Age humanity is fundamentally skewed because we were missing the coastal component. It's as if future archaeologists tried to understand 21st century America but could only excavate sites in the Rocky Mountains. They miss New York, Los Angeles, Miami, Chicago, and Seattle. They'd get a very incomplete picture. Beyond material culture, we've also lost knowledge, the accumulated wisdom of peoples who knew the coastal landscapes intimately and had adapted to them over thousands of years. When their lands were drowned, their knowledge died with them or had to be completely relearned in new environments. And we've lost languages, stories, songs, beliefs, all the intangible cultural heritage that makes human societies unique. Every human culture that was displaced or destroyed by the rising seas was an irreplaceable repository of ways of thinking about and being in the world. The survivors who moved inland and eventually created the great river valley civilizations carried some of this heritage with them, including, perhaps, their flood stories. But much was inevitably lost in the transition. The story of the Ice Age floods isn't just ancient history. It has profound relevance for our present and future. We find ourselves in a similar period of rapid climate change, with ice sheets melting and sea levels rising. Understanding what happened 12,000 years ago can help us prepare for what's coming. Modern sea level rise, driven by anthropogenic climate change, is occurring at a rate that may soon match or exceed the fastest rates during the post-Ice Age period. Currently, sea levels are rising at about 3 to 4 millimeters per year, on average roughly 1 foot per century. But this rate is accelerating as ice melt increases. The Greenland and Antarctic ice sheets together contain enough water to raise sea levels by over 200 feet. Not as much as during the Ice Age, since they're already partially melted, but still enough to completely remake the world's coastlines. While a complete melt would take centuries or millennia, even partial melting could raise sea levels by 10 to 20 feet within this century under worst-case scenarios. And history shows us that ice sheet collapse can occur in pulsus periods of rapid melting alternating with stability. Our vulnerability to sea level rise today is actually greater than it was 12,000 years ago, for several reasons. First, population density. During the Ice Age, Earth's total human population was perhaps 5 to 10 million people. Today, it's nearly 8 billion. Hundreds of millions of people live in coastal zones that would be threatened by significant sea level rise. Cities like Miami, New York, London, Shanghai, Mumbai, and countless others are all built on land that would be partially or completely inundated by major sea level rise. Second, infrastructure investment. Our ancestors could move inland relatively easily. They were mobile hunter-gatherers or early farmers with relatively simple settlements. We have built immovable infrastructure, cities, ports, roads, power plants, and industrial facilities. Relocating all of this would be economically devastating. Third, political boundaries. During the Ice Age, people could migrate to wherever conditions were favorable. Today, national borders restrict movement. Climate refugees from flooded coastal areas can't simply move to higher ground if that higher ground is in another country that won't accept them. Fourth, agricultural dependence. Modern civilization depends on agriculture in specific regions. If sea level rise inundates major agricultural areas, like the delta regions of major rivers, we can't simply shift agriculture elsewhere without massive disruption. Fifth, speed of change. While the post-Ice Age floods occurred over thousands of years, giving societies time to adapt gradually modern climate change is happening faster. The rate of change may outpace our ability to adapt. Despite these challenges, the history of the Ice Age floods also offers reasons for hope. Our ancestors survived the greatest climate catastrophe in human history. Not only survived but thrived, eventually building the civilizations that led to our modern world. This demonstrates human resilience and adaptability. We also have advantages our ancestors lacked. We understand what's happening and why. We have technology they couldn't have imagined. We have global communication and coordination capabilities. We have scientific knowledge of climate systems. We can model future scenarios and plan accordingly. The floods at the end of the Ice Age took people by surprise. No one understood why sea levels were rising or could predict how high they would go. We don't have that excuse. We know what's coming, broadly if not in exact detail. This knowledge gives us the opportunity to prepare, to reduce greenhouse gas emissions and slow the rate of change, to build coastal defenses where practical, to plan managed retreats from vulnerable areas, to develop technologies for adaptation, and to create policies that fairly distribute the costs and benefits of climate action. One of the most concerning aspects of modern climate change is the concept of tipping point thresholds beyond which changes become self-reinforcing and potentially unstoppable. The geological record from the end of the Ice Age provides evidence of such tipping points. The Younger Dryas appears to have been triggered by a relatively sudden event, possibly a flood of meltwater into the North Atlantic that pushed the climate system into a different stable state. The end of the Younger Dryas was equally abrupt, suggesting another tipping point was crossed. Modern ice sheets may have similar tipping points. Once melting reaches a certain rate, it may become irreversible, even if we stop emitting greenhouse gases. This is because several feedback mechanisms can accelerate melting. Ice reflects sunlight back into space, but as ice melts and exposes darker rock or ocean water, more heat is absorbed, causing more melting. This is the ice albedo feedback. As glaciers thin, they flow faster toward the ocean, increasing the rate at which ice is lost. This is mechanical feedback. Warm ocean water can melt ice shelves from below, removing the buttressing effect that prevents land glaciers from flowing into the ocean. This is particularly concerning in Antarctica. Knowing about these tipping points from the geological record helps us understand what to watch for and what to try to avoid. But it also serves as a warning. Once certain thresholds are crossed, the changes may be difficult or impossible to reverse on human timescales. The story of the Ice Age floods also raises profound ethical questions about our responsibilities to future generations. The people living during the floods couldn't have prevented them. These were natural changes, driven by orbital variations and other factors beyond human control. But they had to live with the consequences. We're in a different situation. Modern climate change is largely caused by human activities, particularly the burning of fossil fuels. We have the knowledge and, potentially, the means to prevent the worst outcomes. If we fail to act, future generations will have to live with consequences that we could have prevented. This makes our situation both more hopeful and more morally fraught. We're not helpless victims of forces beyond our control. We're active agents who can shape the future. But that agency comes with responsibility. The Ice Age floods catalyzed the development of civilization, but at the cost of tremendous disruption and the loss of entire ways of life. Do we want to repeat that experience? Can we find ways to transition to a sustainable civilization without the catastrophe first? Finally, the fact that flood myths persisted for thousands of years, potentially preserving memories of real events, tells us something important about human culture and memory. Stories matter. The experiences of our ancestors, preserved in oral tradition and eventually in written texts, shape how we understand the world. The flood myths that appear in so many cultures serve to remind people that the world can change dramatically, that catastrophes can happen, and that survival requires adaptation and cooperation. Today, we're creating our own narrative about climate change, a narrative that future generations will inherit. What story are we telling? Are we the generation that recognized the danger and took action? Or are we the generation that knew what was coming, but failed to respond adequately? The people of the Ice Age had no choice but to adapt to climate change beyond their control. We have a choice. We can reduce emissions, develop sustainable technologies, build resilience into our systems, and create fair policies for managing the transition. But like our Ice Age ancestors, we're also storytelling creatures. The story we tell ourselves about climate change, whether it's a story of inevitable doom, technological salvation, or collective action and adaptation, will shape how we respond. The study of the Ice Age floods is far from complete. New discoveries continue to refine and sometimes overturn our understanding. Underwater archaeology is still in its infancy. New remote sensing technologies, sonar, LiDAR, and magnetometry are making it possible to survey the seabed with increasing detail. Each year brings new discoveries of submerged settlements, landscapes, and artifacts. Climate science continues to improve its models of past and future climate change. Higher resolution ice cores, more sophisticated analysis techniques, and better computer models are providing increasingly detailed pictures of exactly how climate changed at the end of the Ice Age. Genetic studies are revealing new information about human population movements during this period. Ancient DNA, extracted from skeletal remains, is showing how populations mixed, migrated, and adapted to changing conditions. Each new line of evidence adds to our understanding, but also raises new questions. Science is a process, not a finished product, and our picture of the Ice Age floods continues to evolve. The story of the Ice Age floods has inevitably attracted attention from those interested in lost civilizations and ancient mysteries. Could the drowned landscapes of the Ice Age be the historical basis for legends of Atlantis and other lost lands? Plato's account of Atlantis describes an advanced civilization on an island beyond the Pillars of Hercules, Strait of Gibraltar, that sank into the sea in a single day and night. While Plato was almost certainly creating an allegory rather than recording history, the story has captivated imaginations for over 2,000 years. Could Atlantis have been inspired by memories of real drowned lands? Some researchers have suggested that Doggerland, Sunderland, or other submerged regions might have inspired such legends. The timing is roughly right. These lands were drowned during the period when oral traditions could plausibly preserve memories of them. However, most archaeologists and historians are skeptical of direct connections. Plato's Atlantis has many elements that don't match any real drowned landscape. A highly advanced civilization with technologies beyond anything in the prehistoric record. A specific timeline that doesn't match. Geological evidence and geographical details that don't fit any known location. More likely, if there's any connection at all, it's asked that Plato drew on Mediterranean flood traditions, which themselves might have been influenced by memories of real events like the Black Sea flooding, to create his fictional allegory about hubris and the fall of civilizations. That said, the drowned coastlines of the Ice Age may well have supported societies more advanced than we currently recognize. The term advanced is tricky. These wouldn't have been civilizations with writing, cities, and technology beyond their time. But they may have had sophisticated knowledge, complex social structures, and rich cultural traditions. Much of this would leave little archaeological trace, especially underwater. The search continues. Every few years, a new claim emerges about underwater structures that might be ancient cities. Most prove to be natural formations or modern debris. But occasionally, genuine archaeological sites are found beneath the waves, confirming that yes, people did live on these drowned lands. And yes, we still have much to learn about them. Understanding ancient floods also helps us prepare for modern ones. While we're not likely to see ice dam failures on the scale of Glacial Lake Agassiz, smaller versions of this phenomenon still occur. In 2015, a glacial lake in Nepal burst through its ice dam, sending a flood down the valley below and killing dozens of people. Similar events occur occasionally in the Himalayas, the Andes, and other glaciated regions. As climate change causes glaciers to melt, new glacial lakes are forming in mountains around the world. Many of these are unstable, held back by loose debris or ice that could fail catastrophically. Scientists are working to identify high-risk lakes and either drain them safely or build early warning systems for communities downstream. The Missoula floods have become a case study for understanding how massive, fast-moving floods behave. The unique geological features they created are used to train geologists and hydrologists in recognizing evidence of catastrophic floods. This knowledge has applications beyond Earth. Scientists have used their understanding of megafloods to interpret Martian landscapes that show evidence of catastrophic water flows in Mars' ancient past. Increasingly, non-professional scientists are contributing to the study of Ice Age floods and drowned landscapes. Fishermen who work in the North Sea have been reporting artifacts from Doggerland for decades. Scuba divers exploring coastal waters have discovered submerged settlements. Amateur archaeologists using Google Earth and other satellite imagery have identified potential sites for investigation. This democratization of discovery is accelerating the pace of research. Professional archaeologists can't possibly explore every mile of coastline or survey every seabed location. But with thousands of people looking, the chances of finding something significant increase dramatically. Some organizations have created formal programs to engage citizen scientists. These programs train volunteers in how to recognize archaeological materials, how to document finds properly, and how to report discoveries to professional researchers. The result is a valuable collaboration between professional expertise and widespread observation. Behind all the geological data, climate models, and archaeological evidence are human stories. Every drowned settlement represents a community, people who lived, loved, worked, played, raised children, told stories, and made art. Every forced migration represents families leaving homes they had known for generations, carrying what they could, and starting over in unfamiliar lands. We'll never know most of these individual stories, but we can imagine them, informed by our understanding of the broader events. Picture a family living on the coast of Doggerland 10,000 years ago. The grandfather tells stories his grandfather told him about when the land stretched far to the south, where now there's only sea. The fishing is still good, but the beach where they collect shellfish keeps moving closer to their settlement. Every few years, they have to move their homes farther inland. They wonder if their grandchildren will have to leave this place entirely. Or imagine a community in the Tigris-Euphrates Valley, watching the waters of what will become the Persian Gulf slowly rising up the river valley. Rich farmland is becoming marsh, then lagoon, then open water. They move upstream, again and again, each time establishing new settlements and abandoning old ones to the sea. Or picture the terror of someone caught in the catastrophic flooding of the Black Sea. The lake they've known their entire lives suddenly rising, faster than anyone can understand. Entire villages disappearing beneath the waves in days. Panicked refugees streamed inland, carrying whatever they could save, looking for high ground and safety. These were real people, with hopes and fears and the same range of human emotions we experience today. They faced challenges we can barely imagine, and most of them survived and adapted. Their resilience is our heritage. The great floods at the end of the Ice Age fundamentally shaped the world we inhabit today. The coastlines we know, the river valleys where civilizations developed, and the distribution of human populations and cultures, all of these were determined in large part by the events of 12,000 years ago. Even our myths and stories bear the imprint of these events. Flood narratives appear in our oldest literature and continue to resonate in modern culture. Films, novels, and other works continue to explore themes of catastrophic flooding and survival, perhaps because these themes connect to something deep in our cultural memory. The agricultural revolution, the rise of cities, the development of writing and mathematics, and the emergence of complex societies and governments. All of these can be traced, at least in part, to the pressures and opportunities created by the end of the Ice Age floods. We are, in a very real sense, the descendants of the flood survivors. Our ancestors were the ones who adapted successfully, who moved to new lands, and who developed new technologies and social structures in response to changing conditions. Their adaptability and resilience are part of our heritage. As we face our own period of climate change and rising seas, the story of the Ice Age floods offers both warning and inspiration. The warning is clear. Climate can change rapidly. Ice sheets can collapse catastrophically. Sea levels can rise dramatically. And the effects on human societies can be profound. These are not abstract possibilities. They're historical facts, things that have happened before and could happen again. The inspiration is equally clear. Humans can adapt to enormous environmental changes. Our ancestors survived the greatest climate catastrophe in human history and went on to build civilizations. We have even greater resources, knowledge, and capabilities than they did. But adaptation comes at a cost. The people who lived on the drowned coastlines lost their homes, their lands, and much of their cultural heritage. The survivors had to start over in new environments, often in competition with other displaced groups. The social upheaval contributed to conflicts, the emergence of hierarchical societies, and the loss of earlier, perhaps more egalitarian ways of life. We have the opportunity to manage our response to climate change more deliberately than our ancestors could. We can plan ahead, coordinate internationally, invest in adaptation, and work to minimize the damage. But this requires acknowledging the reality of what's coming and taking action despite the costs and difficulties. A geological record is patient and impartial. It shows us what happened without sugarcoating or catastrophizing. Ice melted, seas rose, landscapes drowned, people adapted, civilizations emerged. These are facts written in ice cores and sediment layers and landscapes and DNA. What we do with this knowledge is up to us. As you drift towards sleep tonight, consider the world beneath the waves. Imagine the continental shelves, now covered by hundreds of feet of water, that were once home to forests, rivers, and human communities. Picture the valleys where our ancestors hunted, the beaches where they gathered food, and the places where they raised their children and told their stories. These places still exist, in a sense. The land is still there, just covered by water. The artifacts remain stone tools, pottery, the foundations of structures waiting in the darkness of the ocean floor. The bones of extinct animals lie scattered across drowned plains. And somewhere in those sediments are the remains of people our ancestors who lived through the end of the Ice Age. The ocean keeps these secrets well. The cold, dark water preserves what air and weather would destroy. In some places, underwater archaeology has found organic materials, wood, leather, and rope that have survived for thousands of years because they were submerged quickly and protected from decay. But the ocean is also vast and difficult to explore. We've mapped more of the surface of Mars than we have of the ocean floor. Most of the drowned world remains unseen and unknown. The majority of Ice Age human history lies beneath the waves, waiting for future generations of archaeologists to discover. In a sense, the story of the Ice Age floods is just one chapter in an ongoing story that spans millions of years. Earth's climate has always changed. Ice ages have come and gone in cycles, driven by variations in Earth's orbit and other factors. The Ice Age that ended 12,000 years ago was just the most recent of many. During earlier ice ages, seas fell and rose, coastlines advanced and retreated, and species migrated and adapted. Life on Earth has survived far more dramatic changes than the end of the last Ice Age. But this long-term perspective can be misleading. Yes, Earth's climate has always changed. Yes, life adapts and continues. But individual species can go extinct. Entire ecosystems can be destroyed. Human societies can collapse. The fact that life as a whole survives doesn't mean that we specifically are safe. The people living at the end of the Ice Age didn't think in terms of geological cycles. They experienced the changes as immediate, personal crises that affected their lives and the lives of their children. That's how we should think about modern climate change, not as an abstract geological process, but as something that will affect real people living real lives. The flood myths that survive in cultures around the world serve as warnings from our ancestors. Whether or not they preserve literal memories of specific events, they embody important truths about the world and human experience. Water can be destructive as well as life-giving. The world can change dramatically in ways beyond human control. Survival sometimes requires abandoning what we know and starting over. But humans are resilient and capable of adapting to enormous changes. These myths also tend to include moral and spiritual elements. The floods are often portrayed as divine judgment or the result of human error and hubris. This reflects a deep human need to find meaning in catastrophe, to believe that disasters happen for reasons and that proper behavior can prevent or mitigate them. Modern science gives us a different framework for understanding floods and climate change. We know the physical causes. We can measure and predict. But the moral dimension remains relevant. Are we being good stewards of the planet? Are we taking responsibility for our impact on climate? Are we preparing adequately for the changes we know are coming? The myths can't answer these questions, but they remind us that these are questions humans have always asked when facing environmental catastrophe. If you listen carefully on a quiet night by the ocean, you can almost hear the whispers of deep time, the slow rhythm of geological processes that operate on scales far beyond human experience. The waves you hear lapping at the shore have done so for millennia, though at different points on the land as sea levels changed. The rocks beneath your feet have been worn smooth by water and ice over millions of years. The sand between your toes contains fragments of shells, rocks, and perhaps even microscopic pieces of meteorites that fell to Earth eons ago. Each wave that breaks on the beach is unique, yet part of an eternal pattern. Each tide rises and falls on a schedule determined by the moon's gravity, the same moon that has pulled Earth's tides for billions of years. Each season brings changes in weather, temperature, and daylight that follow patterns established by Earth's tilt and orbit. But within these eternal rhythms, dramatic changes occur. Coastlines shift. Ice sheets grow and shrink. Species evolve and go extinct. Humans build civilizations that rise and fall. The Ice Age floods were one such dramatic change of punctuation mark in the long, slow sentence of geological time. For the people who experienced them, they were life-changing catastrophes. From a geological perspective, they were a brief transition between two relatively stable climate states. Both perspectives are true. The floods were both a human catastrophe and a natural transition. They were both unique events and part of recurring cycles. They were both endings and beginnings. Humans are unique among animals in our ability to remember and plan across long time spans. We can learn from the past and prepare for the future. We can pass knowledge down through generations. We can change our behavior based on events we've never personally experienced. This is both a gift and a burden. The gift is that we're not doomed to repeat the mistakes of the past. We can learn, adapt, and prepare. The burden is that we have to live with the knowledge of what might come. We can't simply live in the present moment like other animals. Our ancestors who survived the Ice Age floods passed down their experiences through stories. They wanted their descendants to remember what had happened and to be prepared if it happened again. They were, in effect, trying to warn us. Are we listening? Do we recognize the parallels between the past and our present situation? Are we taking seriously the warnings that both ancient myths and modern science are giving us? These are uncomfortable questions. It's easier to ignore them, to assume that catastrophe won't happen in our lifetimes, that someone else will solve the problems. But the geological record and the myths preserved from it tell us that this is a dangerous assumption. As you prepare for sleep, consider that you're lying on a planet that is always changing. Beneath you, tectonic plates are slowly moving, though you can't feel it. Around you, weather systems are swirling, driven by energy from the sun. Above you, the atmosphere is a thin, fragile layer that makes life possible. This planet has been through dramatic changes before ice ages and warm periods, massive volcanic eruptions and meteorite impacts, and the rise and fall of mountain ranges and seas. Through it all, life has persisted, adapted, and evolved. Our species is young, only a few 100,000 years old. But we've already survived one ice age and the dramatic climate changes that followed. We've adapted to environments from Arctic tundra to tropical rainforests to high-altitude mountains. We've developed technologies that allow us to live in places that would otherwise be uninhabitable. This adaptability is our greatest strength, but it also comes with responsibility. We've become so successful that we now affect the planet at geological scales. Our actions are changing the climate, altering ecosystems, and influencing what the future Earth will be like. The people of the Ice Age had no choice in the climate changes they faced. We do have choices. We can reduce our impact. We can prepare for changes. We can work together globally to address challenges that affect all of humanity. Or we can ignore the warnings and hope for the best. But if we make that choice, we should at least be honest about what we are risking and what our descendants will have to deal with as a result. Much of history is sleeping buried underground, submerged underwater, or simply forgotten because no one recorded it. The drowned coastlines of the Ice Age are sleeping beneath the waves. The societies that lived are sleeping in archaeological sites we haven't yet found. The knowledge they possessed is sleeping in myths and stories we haven't yet fully understood. Occasionally, we wake up small pieces of this sleeping history. A fisherman's net brings up a worked stone tool from the seabed. An archaeologist finds a settlement buried under centuries of sediment. A geneticist extracts ancient DNA that tells us about human migrations we didn't know about. A climate scientist discovers a pattern in ice cores that reveals a sudden climate shift. Each discovery is like waking up a small part of the past. And each time we wake up a piece of history, we learn something that helps us understand our present and prepare for our future. The Ice Age floods are partially awake now. We've learned a great deal about what happened, when it happened, and why. But much remains sleeping, waiting for future discoveries and future researchers who will have better tools and new questions to ask. Your own sleep tonight will be brief, a few hours of rest before waking to another day. But the sleep of history is long, thousands or millions of years before the next discovery brings another piece of the past back to life. In dreams, we sometimes find ourselves underwater, swimming through submerged cities, walking on ocean floors, breathing water like air. These dreams can be peaceful or frightening, but they often carry a sense of exploring hidden or forgotten places. Perhaps these dreams connect to something in our deep memory, a recollection of the drowned world that our ancestors knew. Perhaps they reflect an unconscious awareness that much of human history lies beneath the waves, forgotten but not entirely gone. Or perhaps they simply the mind's way of processing our relationship with water, essential for life, but also potentially dangerous. Water that gives us life to drink, but can also drown us. Water that sustains agriculture, but can destroy it in floods. Water that enables trade and travel, but also divides continents and limits where we can live. Our relationship with water is complex and contradictory, and it is fitting that the story of human civilization is so deeply intertwined with floods, both the catastrophic floods at the end of the Ice Age and the annual floods of great rivers that enabled agriculture and cities. As you sleep tonight, you might dream of water. If you do, remember the drowned world beneath the seas. Remember the people who lived there, who witnessed the rising waters, who survived and adapted and passed down their stories. They were our ancestors, and their resilience lives on in us. Every catastrophe eventually ends. The Ice Age floods, dramatic as they were, eventually subsided. Sea levels stabilized. The climate settled into a new equilibrium. The survivors rebuilt their lives in new lands. And from the ashes, or rather, from the flood, something new emerged. The pressure of adaptation drove innovation. The concentration of populations created new social structures. The challenges of new environments sparked creativity. The civilizations that emerged after the floods went on to accomplish remarkable things. Monumental architecture, sophisticated art, complex mathematics, detailed astronomy, and beautiful literature. Humans went from small bands of hunter-gatherers to city builders, philosophers, and eventually space explorers. This doesn't mean the floods were good. The suffering and loss were real, and we shouldn't romanticize catastrophe. But it does show that humans have an extraordinary capacity, not just to survive disaster, but to build something meaningful from the wreckage. We face our own challenges now: climate change, rising seas, and the prospect of displacing millions of people from coastal regions. Like our Ice Age ancestors, we'll have to adapt. But unlike them, we have knowledge, technology, and the ability to coordinate globally. What will we build from this challenge? What innovations will emerge from the pressure to adapt? What new social structures will we create? What stories will our descendants tell about how we responded? These questions remain open. The future isn't written yet, but the past shows us that humans are capable of remarkable resilience and adaptation when faced with seemingly impossible challenges. There is a strange comfort in thinking about deep time, the vast stretches of history that preceded us, and the equally vast future that will follow. Our individual lives are brief, a few decades, if we're lucky. Our anxieties and problems can feel overwhelming in the moment. But set against the background of geological time, even catastrophic events are just moments, brief episodes in an ongoing story. The Ice Age floods were dramatic and traumatic for the people who experienced them. But from the perspective of deep time, they were simply a transition Earth, shifting from one climate state to another, as it has done many times before and will do again. This perspective doesn't diminish the real suffering of individuals, but it can provide comfort. You are part of something much larger than yourself, a story that extends back millions of years and forward into a future we can barely imagine. Your problems are real but temporary. Your pain is valid but will pass. You, like everyone who came before and everyone who will come after, are doing your best to navigate a world that's always changing. The people who lived through the Ice Age floods probably couldn't imagine what their world would look like thousands of years in their future. They couldn't have predicted the rise of cities, the invention of writing, or the development of science and technology. They just tried to survive and provide for their children. We are in the same position. We can't fully predict what the future will bring. We can only do our best to meet current challenges and pass on something good to future generations. And sometimes that means simply surviving, adapting, persisting, and carrying on despite difficulties. Our Ice Age ancestors managed it, and so can we. And so we come to the end of our journey through deep time, from the frozen world of 20,000 years ago, through the catastrophic floods that transformed Earth, to the emergence of civilization and our present day. The drowned world sleeps beneath the waves, keeping its secrets. The ice cores rest in freezers, their ancient air trapped in bubbles, waiting to be analyzed. The flood myths continue to be told and retold, adapted for new audiences, but retaining their essential message about water, catastrophe, and survival. The story of the Ice Age floods is both ancient history and a present warning. It shows us what Earth is capable of, how quickly climate can change, how dramatically landscapes can be transformed, and how profoundly human societies can be affected. But it also shows us what we're capable of: adapting, surviving, building something new from disaster, and preserving memory across thousands of years through stories and traditions. As you close your eyes tonight, picture the world as it was at the end of the Ice Age. The great ice sheets are melting. The glacial lakes are building behind ice dams. The coastlines are slowly drowning beneath rising seas. The communities of people watching their world transform, telling stories to preserve memory and adapting to survive. They made it through. They carried on. Their descendants thus eventually built a global civilization. And now we face our own challenges. equipped with their legacy of resilience and our own tools of knowledge and technology. Sleep well, knowing that you're part of this long human story. Dream of deep water, ancient floods, and drowned worlds beneath the waves. Dream of ice and fire, of catastrophe and survival, of endings and new beginnings. And wake refreshed, ready to face whatever floods, literal or metaphorical, your own life might bring. Because, like your ancestors before you, you carry within you the resilience of those who survived the greatest climate catastrophe in human history. The floods came. The world changed. Life continued. And so it will be again. Rest now, child of the flood survivors. Tomorrow awaits, with all its challenges and possibilities. But tonight, you sleep on a planet that has seen far greater changes than anything we face today, and endured. The ancient world beneath the waves sends its blessing. Adapt, survive, remember, and carry on. Good night.